Welcome to this video. And in this video, I discuss the synthesis of one-port RL networks. We discuss the synthesis of one-port RL networks. For any network to be implementable using RL components, it must meet the following properties. Property number one, all the poles and zeros must lie on the negative real axis interlaced. All the poles and zeros, they must lie on the negative real axis and they must be interlaced. So this is what we also noted with RC networks. All the poles and zeros, they fall on the negative real axis and they interlace. Number two, the singularity that is closest to the origin is a zero. So a zero is closest to the origin. A zero is closest to the origin. And lastly, all the residuals of the poles must be real and positive. The residuals of the poles, we are saying this must be real and negative. So for any transfer function to be implementable using RL networks, all the poles and zeros must fall on the negative real axis and interlacing. A zero should be closest to the origin. That means a pole is closer to negative infinity. And all the residuals of the poles must be real and negative. That is to mean if we are to obtain the partial parts of the given transfer function, the constants on the numerator must be negative. Let's take an example and test a transfer function for properties of RL networks. Suppose you have an impedance transfer function Z of S given by 2S squared plus 8S plus 6 divided by S squared plus 8S plus 12. From this transfer function, we can write this as 2 into S squared plus 4S plus 3. We factor out 2 on the numerator, divided by S squared plus 8S plus 12. Let's put these into their factors. So this can be written as 2 into, for the numerator, notice the terms are 1 and 3. So we'll have S plus 1 into S plus 3. And for the denominator, the roots are 2 and 4. That is 3 and 4. This is, sorry, 2 and 6. 2 and 6, this being 8 and 12, they must be 2 and 6. So you can write these as S plus 2 into S plus 3. From which we notice that our poles are S is equals to -2 and -3. And our zeros are S is equals to -1 and S is -3. Notice this was supposed to be 6. This is 6. And therefore, the pole should be at -6, not -3. If we are to sketch these on an S-plane, a plane of real to imaginary axis, can have this as 0, 1, 2, 3, 4, 5, 6. These are negative. We have the poles at -2 and -6. So we have a pole here at -2 and -6. We have a 0 at -1 and -3. You notice that all the poles and zeros fall on the negative real axis, and the interlacing. We have a 0, a pole, a 0, a pole. Property number 1 is met. Property number 2 is that a 0 should be closest to the origin. So we have a 0 at -1, which is closest to the origin as opposed to all the other singularities. Next, we need to determine the residuals of the poles. To determine the residuals of the poles, we need to put our transfer function into partial fraction form. But because the order of the numerator and denominator are the same, we first perform division. We divide 2s squared plus 8s plus 6 divided by s squared plus 8s plus 12. This will give us 2 into 2s squared plus 16s plus 24, and the difference will be minus 8s minus 18. We can proceed and write our transfer function as z of s is 2 plus minus 8s minus 18 divided by the denominator, which is s plus 2 into s plus 6. That's our transfer function, which we can write as 2 plus a over s plus 2 plus b over s plus 6. This will give us a be minus 8s minus 18 divided by s plus 6 when s is -2. And this one will give us -2 over 4, which is -1/2. Our b will be minus 8s minus 18 divided by s plus 2 when s is -6, which will give us 30 divided by -4, which is -15/2. Both A and B, which are the residuals of the poles, -2 and -6, are negative. And therefore, property number 3, which requires that the residuals of the poles to be real and negative, is met. And therefore, the transfer function meets all the properties of RL networks, and therefore can be implemented using one-port RL networks. Let's proceed to implement using the 4 methods. The first method is the Foster series. The Foster series method. In the Foster series method, we said that all the components are in series, and if there is any parallel arrangement, it is in series with the entire network. It should have a resistor, an inductor, resistor-inductor parallel arrangement, and all these are in series. This is our Foster series network. All the components are in series. To determine to implement using the Foster series method, we use partial fraction expansion of our transfer function. But we've noted that if you use the partial fraction expansion, you'll end up with negative residuals. And that would mean that when you compute the component values, some component values will have negative values, which doesn't happen in reality. And therefore, when we want to implement the transfer function, we do not expand the transfer function into partial fraction directly, but rather we first divide it by s, expand it into partial fraction form, and then multiply the resulting partial fraction expansion by s to get back our transfer function. Let's consider our transfer function z of s, which was given by 2 into s plus 1, s plus 3 over s plus 2 into s plus 6. We first get our z of s divided by s into partial fraction, which will give us 2 into s plus 1 into s plus 3 divided by s into s plus 2, s plus 6. This will give us three partial parts, a over s plus b over s plus 2 plus c over s plus 6. We determine the values of a, b, and c, and you'll notice that the value of a will be a half, b will be a quarter, and c will be 5 over 4. So you can determine the values of the constants a, b, c, and therefore we can write our z of s over s is a, which is a half over s, plus b, which is a quarter over s plus 2, plus c, which is 5 over 4 over s plus 6. Next, we multiply all the partial parts by s so as to get back our z of s, which will give us a half plus a quarter s over s plus 2 plus 5 over 4s over s plus 6. Once we have these partial parts, then we consider the first part. The first part indicates a resistor whose resistance is a half ohms. Being a constant indicates a resistor. Then the combination of s over s plus 2 gives us an inductor resistor parallel combination as follows. So you have a resistor, an inductor, and a resistor in parallel. This is SL and this is R, whose impedance will be given by SL times R over SL plus R, which we can write as you divide by L to make the coefficients of S in the denominator 1, it will be SR over S plus R over L. And this is what we will be comparing with each of the parts that we have. Let's take the first part, which is a quarter S over S plus 2. We compare this with SR over S plus R over L, from which you'll notice that R will be a quarter ohms, and our R over L is equals to 2. The constant here will be equal to the constant here, from which you notice then our L, our L will be R over 2, and which will give us an 8 Henry. Next, we compare 5 over 4s over s plus 6. We compare this again with SR over S plus R over L, from which you notice that our R, which is the coefficient in the numerator, will be 5 over 4 ohms. And from the denominator, you can write R over L is 6, from which our L will be 5 over 24 Henry. At the end of the day, then we can implement our network as follows: a resistor, a set of resistor inductor parallel combination, and another set of resistor inductor parallel arrangement. The resistance, as we noted, is half ohms from our partial fraction expansion. This is 1/2 ohms. The resistor here is a quarter ohms. This is 1/8 Henry. This is 5/4 ohms. This is 5/4 ohms. And this is 5/24 Henry as our inductance. And that is the Foster series implementation of the RL network. And the second method is the Foster parallel. Foster parallel. In the Foster parallel, all the components are in parallel, and if there is any series arrangement, it's in parallel with the entire network. That means we can have a resistor, an inductor, and then a resistor series arrangement with an inductor, and all the components are in parallel. If there is any series arrangement, it is in parallel with the entire network. And this is the Foster parallel network. To implement the Foster parallel, we said we use the admittance transfer function expanded in partial fraction form. For our case, our impedance transfer function was given by 2s squared plus 8s plus 6 divided by s squared plus 8s plus 12. The admittance is the reciprocal, which is the s squared plus 8s plus 12 divided by 2s squared plus 8s plus 6. Because the order of the numerator and denominator are the same, we first perform division to get s squared plus 8s plus 12. We divide this into 2s squared plus 8s plus 6. We get this as a half into s squared plus 4s plus 3, and the remainder is 4s plus 9. That means our y of s can be written as a half plus 4s plus 9 over 2s squared plus 8s plus 6, which you can write as a half plus 4s plus 9 divided by 2 into the terms which were s plus 1 into s plus 3, which you can also write as a half plus, then we take the 2 up to get 2s plus 9 over 2 over s plus 1 into s plus 3. We need to put this into partial fraction form. So I need 2s plus 9 over 2 over s plus 1 into s plus 3, which you can write as a over s plus 1 plus b over s plus 3. If you evaluate the values of a and b, a will be 5/4 and b will be 3/4. That means we can write those terms as 5/4 over s plus 1 plus 3/4 over s plus 3, from which then we can write our admittance y of s to be a half plus 5/4 over s plus 1 plus 3/4 over s plus 3. This is admittance being a constant, that means its conductance. If it's conductance, then the resistance is 2 ohms, because conductance is 1 over R, which we compare with 1 over 2, and therefore the resistance is 2 ohms. These two parts means we have an inductor resistor series arrangement in admittance form. If you have a resistor and an inductor in series as R SL, the impedance will be given by SL plus R. The admittance will be the reciprocal, which is 1 over SL plus R, which we can write as, we make the coefficient of S on the numerator to be 1, we divide by L to get 1 over L over S plus R. And this is what we compare with our next two partial parts. For 5 over 4 over S plus 1, we compare this with 1 over L over S plus R. 5 over 4 is the same as, is equal to 1 over L, and therefore L will be the reciprocal, which is 4 over 5 Henry. This is R over L. Then R over L is 1, R over L is 1, and therefore R will be equal to 4 over 5. Sorry, it will be equal, because R will be equal to L. That means then our R will still be equal to 4 over 5 ohms. The next one is 3 over 4 over S plus 3. We compare this with 1 over L over S plus R over L, from which we get our L to be 4 over 3 Henry, the reciprocal of the numerator here. And then our R over L is 3. That means R will be 3 times L, 4 over 3, which is 4 ohms. And those are the parameters of our given circuit, from which we can draw our circuit as a resistor in parallel, whose resistance is 2 ohms, a resistor inductor series, and another resistor inductor series, but all in parallel with the entire network. In the first one, both of them are 4 over 3 ohms and 4 over 3 Henry. Then in the other one, our inductance is 4 over 3, but resistance is 4 ohms. So this is 4 ohms, and this is 4 over 3 Henry. And this is our Foster parallel implementation of the one-port RL network. Number 3 is the Cauer 1 network. In the Cauer 1 network, we said we have series parallel arrangement of the components alternating each other. So we would expect that we have a resistor in parallel, in series, an inductor in parallel, resistor, inductor arrangement like so. To obtain the component values for our network, we use the continuous fraction expansion, having written our transfer function in descending powers of S. Notice our Z of S was given as 2S squared plus 8S plus 6 divided by S squared plus 8S plus 12. This is already in descending powers of S, and therefore we can proceed to compute the continuous fraction expansion for it, which we can write as 2S squared plus 8S plus 6. We divide these into s squared plus 8s plus 6. So we need to get 2s squared plus 16s plus 12, and the difference will be minus 8s minus 6. Next, we divide this into s squared plus 8s plus 6. To get s squared from negative 8, then I multiply that with negative 1 over 8s, and I'll get s squared. Then this becomes plus 3 over 4s, and then I get the difference. But you notice that this term will give us a negative term. And if you try to look at this term, this will correspond to a resistor, and this corresponds to an inductor. But as you can see, the value of the inductance is negative, and this will not be implementable. And therefore, the Cauer 1 network for the RL one-port network will not work, because we'll obtain some of the components to have negative values, which in reality does not happen. Lastly, we look at the Cauer 2 network. For the Cauer 2 network, we expect that we have inductors in series and resistors in parallel. This is what we expect based on our previous discussion. And again, to determine the component values, we need to expand our transfer function in continuous fraction expansion, but having written our transfer function in ascending powers of s. So our z of s was given by 2s squared plus 8s plus 6 divided by, this is divided by s squared plus 8s plus 12, which we can write in ascending powers of s as 6 plus 8s plus 2s squared divided by 12 plus 8s plus s squared. Then we proceed to determine the continuous fraction expansion for it, which we can write as 12 plus 8s plus s squared. We divide this into 6 plus 8s plus 2s squared. So I need 6 from 12, and therefore I multiply that by a half to get 6 plus 4s plus a half s squared, and the difference will give us 4s plus 3 over 2s squared. Next, we divide these into 12 plus 8s plus s squared. I need 12 from 4s, so I multiply that with 3 over s. 3 over s, that will give us 12 plus 9 over 2s, and the difference will give us 7 over 2s plus s squared, which we divide into 4s plus 3 over 2s squared. I need 4s from 7 over 2, and then I multiply this with 8 over 7. I multiply with 8 over 7 to get 4s, so that this is 4s, and the difference will be 3 over 2s squared, which I will divide into 7 over 2s plus s squared. To get 7 over 2 from, sorry, I should have had here, when I multiplied 8 over 7 by this, I should have had this as 8 over 7s squared, so that the difference The difference here will be 3 over 2 minus 8 over 7. 3 over 2 minus 8 over 7. This is 3 over 2 minus 8 over 7. The LCM is 14 to get 21 minus 16, which is 5 over 14. 5 over 14 s squared. So to get 7 over 2 from 5 over 14, I multiply this with 49 over 5s. And this will give us 7 over 2s. The difference is s squared, which I will divide into 5 over 14, which I divide into 5 over 14 s squared. And you can notice then the term will be 5 over 14. Okay. Next, we can now draw our circuit with the following considerations. The first term is a constant, and we expected to have a term that has S being an inductor. That means the Cauer 2 will start with a resistor whose resistance is 1 over 2 ohms. 3 over S will correspond to admittance due to an inductor, which is 1 over SL, 1 over SL compared to 3 over S, and therefore we'll have an inductor whose inductance is a third Henry. Next, we have a constant, 8 over 7. That means another resistor whose resistance is 8 over 7 ohms. 49 over 5s, another inductor in parallel, whose inductance is 5 over 49 Henry. And finally, we have a constant 5 over 14, which means it's a resistor whose resistance is 5 over 14 ohms. And this becomes the Cauer 2 implementation of the one-port RL network given the transfer function. As you noticed, we'll have resistors in series and inductors in parallel for the Cauer 2 implementation of the RL networks. Otherwise, thank you for watching the video, and that is the end of my discussion for the one-port RL networks.